And let's take a look at the syllabus. I have changed S1 to just be sections 1 and 2, which is mainly 2. And then these new notes are for section 3, which I've broken out separately. And then here's the lecture. Now just to go back and talk about the assignment for a second. The way I want you to name your assignment is your mix email name, followed by, I told this in my other class, and I better distinguish these between this class and the other class. So I want you to mix email name followed by 523, even if you're in 423, no matter what you're in, followed by 523. Dot 1 dot RMD.
Can we do RNW?
Well, no. If you're doing RNW, you can do it that way too. So you're, but you would have had to convert the homework to that. If you did that, that's fine. So your name from mixed, the name to the left of the @ sign, followed by 523 dot 1 dot RMD or dot RNW, whichever you use. And I'd like you to send me both the dot RMD with the HTML file also, or the dot RNW with the PDF file, whichever way you do it. So I want both files. That's just in case I have trouble running your code, like if you have an error. If you've got a previous version that you've run that has part of the output, then send it along. I do intend to actually execute your code, though. So hopefully you don't have any files that I don't have. But that's another reason why I want the HTML file or the PDF file. Is that clear? Now, I would describe this book as sort of being kind of high up in the sense that it talks about some fairly advanced topics, and then it doesn't necessarily give lower level examples, which maybe you want. And then on the other hand, it may have some homework problems which have lower example problems. So for example, one of the homework problems dealt with using repeat or a while. And you may not have any examples of actually where that was done. And so I would first of all mention that if you're using repeat and while, you probably do not want to include within it a for loop. In other words, it's not to say that you couldn't put a for loop within a repeat or while, but generally speaking, you would have if statements to sort of break out of it. So one of the paradigms you can follow is that you can have an initialization like I equals 1, and then you have the repeat, and then you can increment the repeat, such as I equals I plus 1 or I equals I plus 2 or whatever. So that's another paradigm. And then you can have if statements that give you an indication about whether or not you should continue or break out, say using next or break. So there are various ways you can solve this problem. It'd be interesting to see how you approach it. But again, I wouldn't use a for loop inside of a repeat or a while. It's not to say you can't. In fact, you can nest for loops within for loops. You can have 2 levels and so forth. So it's not to say you can't, but you don't really need to do it in that particular problem. I did want to show you. I did want to show you a book that I bought from O'Reilly that you might want to take a look at. So at any rate, before you leave this page, you might want to download the Chapter 3, Section 3 notes, because they're broken out from the. I've redefined C3S1. It no longer contains the stuff for Section 3. I've broken it out separately. Ultimately, my goal is to kind of break out all the sections separately and have shorter little segments, but that's probably not going to happen this semester. So what I wanted to do, there are a lot of books out there. There are a lot of books available which you might want to look at. Some are better than others. I've bought some, and here's my ebook collection. And so one I found, if you buy from O'Reilly.com, you can get the ebook by itself, and usually you can get the ebook and the print book for not much more than the ebook or the print book individually. And plus you get it in PDF, and it comes in various formats, including EPUB or PDF. Both of those, for example, are supported by the iPad, and the Nook supports EPUB and so forth. Kindle has its own format, but I think O'Reilly usually supports it. But it's also true that if you have another tablet, like the iPad, you can run the Kindle app on it, or the Nook app also. In other words, both Kindle and Nook have apps that run on things like the iPad. At any rate, this book I found to be fairly good. And it's called Learning R. Well, maybe I'll leave it this way. If you look at the index, then you'll see that, for example, in Chapter 9 talks about advanced looping, and so it talks about looping over lists and various other topics. But it also, maybe I should do this single page. It also gets into things like repeat and while. So this book gives things at a somewhat lower level, and it actually doesn't get into some of the high level concepts, but this book might be a good book that sort of complements what we're doing. I did want to mention that it does talk about environments, and so this might give you a slightly lower level version of what an environment is. So again, this is a book that I think is pretty good. And by the way, here's some basic stuff on flow control and loops. I'm trying to remember where this gets actually into some data, but what I'm looking for, I'm not sure where it is. It's not what I'm looking for. Oh, maybe this is what I'm looking for. Chapters. I wanted just to mention this before I get back to S3 classes. This is summarizing the class systems that are built into R. And notice that it says S3 is a lightweight system for overloading functions. That is, calling different versions of the function depending on the type or the class of the input. And that's what we're talking about right now in this particular section 3. And then they describe S4 as a fully featured object-oriented programming system that is clunky and a bit tricky to debug. So that's what you have to look forward to in the next section. But here's what I'm interested in, is reference classes are the modern replacement for S4. And the original author of S3 and S4 classes, his name is John Chambers. And he is actually writing that. And the problem is that this is just, he's writing a book on it, but I don't think it's out. And so there's not much documentation on doing reference classes. But if, in fact, it's good, then that will be welcome, because S4 is a bit clunky, it's true. It's not as clean as what I would like to see. They do mention 3 other classes: Proto, which is what's called a prototype-based system, .R0.ROO, which is a full-fledged, it converts S3 into a full-fledged op system. And then there's another OOP, which is now defunct. There are people that really like Proto. So if you look at the graphics in ggplot2, which is a very massive graphic system, they use Proto. And so a lot of people really like that system. So at any rate, I would be a little hesitant to use certainly the last 2 mentioned there, because, again, someone wrote an extension and, you know, it's not clear how long it's going to be supported and so forth. But the first 3 are certainly going to be supported for a long time. And probably Proto is, and the reason I think it is because there are some fairly big projects using Proto. So that would be another system. This book does actually go in, it talks about S3 classes, so this may help what we're talking about today, because it does so at a bit left, it does so, but it does it in about 3 pages, or 2 pages. So again, it's very brief. But he does talk a little bit about reference classes, and so that may give you some indication. I'm not going to do this in this class because it's a little bit premature. He actually gives more on reference classes than he does S3. So I think that this may be promising as we move forward, but right now it's probably premature to be teaching reference classes. I just want you to know that reference classes may start replacing S4 classes, particularly if there's an easy way to transition from S4 to reference classes. So this is one book that you might want to consider getting. You know, if you wanted to find it, you can go to O'Reilly.com, and they always have sales, so you can usually get things cheaper. But the thing that I wanted to mention, so here's Learning R. Now here's the various books. All of these books right here, those first 3 in particular, but there's another book on RStudio, and I think it's an O'Reilly book. At any rate, Learning R is the book I was just talking about. R in a nutshell is more of a reference book, but it's very complete. But it's not necessarily the best sort of book to learn R with, but it is very complete. It's more like a reference manual. And then Learning RStudio. Again, I don't know that book. There's another book on RStudio. And you can see there are a number of books. Now, if you go into various publishers, like the two publishers that have the most books using Aura is CRC Press. Has a lot of books, which is what our book is, but they have a lot of books on Aura. And then the other is Springer Verlag, which also has a lot of books on Aura. Okay, so I'm just giving you this again. If you click here, you see that buying the print and ebook is not much more than buying the ebook or the print. So if you kind of still like paper in your hands, you can get both here. One of the things I like about these publishers is that they periodically update the ebooks. So you'll get an email saying there's been an update to this book. And now if it's a second edition, you may have to buy it again, but if there are updates, not only correcting errors, but there may be some enhancements, you typically can get an account, and your account, you can always go in and see what you have, and you can always see your edition that you have versus what the latest edition is. So you can always download it. And you can download it in PDF, and there are no restrictions on it. So you can put it on multiple devices. I shouldn't tell you that, but it's true. They're trusting. Any questions on that? So if you need some supplemental help, I'm just pointing out there are a number of books. There are a number of books that are good, but some of them are more reference manuals, which may not be too much help for you. Okay, let's go into RStudio now. I'll probably put a link on my, not on the schedule, but on the syllabus page. I'll probably put a link into that Learning Aura book. Of the ones I've found, that seems to be fairly good. So what I want to do now is to go into 523, and I'm going to go into chapter 3, and I'm going to look at C3S3, the .omd file. And before I go any further, I'm going to clear the console, and I'm going to set the working directory to where we are, and then I'm going to switch over to the workspace and clear it. So it's kind of your initial steps you probably should do every time to kind of get things in the right place. So I'm going to go ahead and knit this so we can take a look. I'm not going to repeat everything I said last time because we did actually start section 3 last time. And so I'm sort of going to skip through this first part. We went through some, as you remember, we went through an example. Where we were creating two classes, a passenger class and a frequent flyer class, which extended it. So now, in this particular case, back in section 2, we actually did that using the S4 method. Here, we were actually creating these same classes more informally in S3. And just to show you what we did, and maybe I'll start at that point, we took, let's see, am I in the right place? Yeah. I created an instance with a list, and that's often the way you do things in S3 classes, is you use the list function. So I'm creating X, and then I'm simply going to say the class of X is passenger. And if I print X out, it prints it out as a list. Now again, in S3, that's often the way we represent the objects is by list. And I'm going to do the same thing for Y. I'm going to make it a frequent flyer. In other words, you notice here I have a vector, a character vector, and it says frequent flyer as the first element, and then passenger. And what I'm doing is specifying multiple inheritance here. I'm specifying the frequent flyer. It's a fast frequent flyer which inherits from passenger. Then if I look at Y, in addition, I have a frequent flyer number. And then if I say, okay, X inherits from passenger, but notice that X does not inherit from frequent flyer. Whereas Y inherits from passenger, and it also inherits from frequent flyer, because this particular person is not only a frequent flyer, but that person is also a passenger. So, any questions? So again, we can actually construct these a little bit more formally than here, but I was just giving this as an example. And again, isObject, we talked about that last time, tests whether or not R is, the R object has a particular class attribute. So we have inherits, so we can say, does this inherit from a class? And I also have isObject, does it inherit from a particular class? I talked again about implicit functions, and that is one of the problems of R. If someone said, oh, I'm going to write a new system, would you do it exactly the way R is done now? Well, there are a couple legacy things. There are objects in R that preceded object-oriented programming, like matrices and arrays and functions. All of those preceded the object-oriented programming paradigm. So it's kind of a retrofit. And therefore, we have some objects in R that are implicitly defined in terms of classes. And those three that I mentioned, the matrix, the array, and the functions, are internal to R, and they are implicitly defined in terms of the class structure. And so the problem is that if I use something like class, I don't necessarily get those implicit objects to print out. So we have to be careful about, if I'm looking for the particular class, the implicit classes may not show up. And so when I'm testing for it, I have to be careful. Okay. Now last time, I think near the end of class, we talked about this GOM example. And so that's a nice example to go through. GOM along with LM and many, in fact, if you look at R, it has very, very powerful functions for modeling. LM and GOM are the only two of a large group of classes. There are many others. So, LM means linear model. And by linear model, I mean any model that's linear in the parameters. So that includes things like multiple regression. It includes the analysis of variance. It includes the analysis of covariance. So it includes all of those types of models. GOM is generalized linear model. So it extends the linear model. The linear model is sort of based on the idea of a normal error. But suppose you have count data and your error term is Poisson. And so then I would have a Poisson regression. But Poisson regression is not a linear model. It's linear in some ways, but it's nonlinear. And it's partially linear and partially nonlinear. It's not completely nonlinear, and that is another class, nonlinear models. But it is nonlinear in terms of what's called a link function. And so you have a lot of the characteristics of a linear model in a generalized linear model, and therefore a GOM inherits from or extends the linear model. Because the algorithms we write for the linear model can be reused in the GOM model. So there's a certain efficiency in having GOM inherit from or extend the linear model. It's more specific though. So this was an example that illustrated that. So let me get back now to something that's new. If you're doing bioinformatics programming, one of the most common data structures you're going to encounter is what's called an expression set. And an expression set is a rather complex object that typically includes both the genomic data and what we call the genotype type data, as well as the phenotype type data. So the phenotype is what you can actually observe, sort of the larger characteristics of, say, an organism, whereas the genotype data, and in particular what we'll be doing, will be what we'll be measuring in this example. But we won't be measuring, we're going to simulate it, but it will be the gene expression data. That is, how much the particular gene expresses. And as you may know, that if, say, you're comparing two groups and one's a cancer group, certain genes may be turned on and express more than others. And so you're trying to find maybe the few genes out of maybe thousands that differentiate the cancer patient from the non-cancer patient. Once you find those genes, those are called biomarkers. Of course, sometimes this is done in terms of a protein, not a gene. So, for example, PSA is a biomarker for prostate cancer. But PSA is a protein, not a gene. But a lot of the techniques we're learning here for genomic analysis can also be used for proteomics. So if we're studying proteins instead of genes, then most of the techniques we're learning are applicable there. There are some differences in terms of the data. And of course, the underlying alphabet for genes is different than the underlying alphabet for proteins. So, what am I interested in doing? Well, a lot of times you want your data structure to be self-describing. So expression set is a self-describing class in the bio-based package. Now, what we're going to do, and it's fairly, it has a lot of information, and not only that, these expression sets often are pretty big. And the reason they're pretty big, it's not because we often talk about the N and P problem. The N corresponds to the number of cases or the number of rows, or in this case, let's say the number of patients. Whereas the P problem talks about the number of variables. And in the case of genomics, maybe the number of genes. So we have an N and P. If we think of it as a matrix, usually we represent it as the number of N represents the number of rows and P represents the number of columns. So classical statistics, we would describe typically for the case that N is bigger than P. We have more observations than we have variables. In genomics, it's the opposite. In fact, P is often a lot bigger than N. So this actually raises a bunch of questions. But you could, if we then represent N rows and P columns, then we may end up having 5,000 columns and maybe 100 rows. Maybe we have 100 patients, and for each patient, we've done a microarray experiment on each patient, and so we know their expression of all 1,000 or 5,000 or however many genes we're looking at. And so with these microarray experiments, we have what we call large P, small n. Now, if you're talking about sort of computational statistics, there are a number of cases. There's the large N, small p problem. That is, you have a lot of data, but your number of variables is not so great. Now, that problem, generally speaking, is not too difficult to handle, but it can become difficult to handle if you exceed the physical memory of your computer. And that can happen. So if you exceed the physical memory of your computer, then how do you analyze it? Because R, by default, does everything in memory. Well, there are lots of ways in R to get around it. So in other words, you can use R for big data. But you also have the big P small n problem, which is bioinformatics to a large degree. The large P, small n. A lot of bioinformatics problems fall in that realm. So our classical techniques often don't work. You know, we have to. So in other words, there's a whole new focus on statistical methodologies to deal with this. So just let me give you a simple case. Suppose that you have 100 rows, and 50 of them are controls, and 50 of them are prostate cancer patients, and then you have lots of genes. And you're trying to get the gene signature for prostate cancer, so you want to look at all 1,000. So you say, okay, I only have 2 groups, right? I'll simply do a t-test on every one of my 1,000 genes. Okay. Now let's suppose there are no differences. What is the probability that I find at least one difference? Testing at the 0.5 level each one. Well, it's 1 minus the probability that you find none. So it's 1 minus 0.95 to the 1,000th power. So the problem is that the probability you find at least one by chance is quite high. In fact, the probability you'll find multiple ones is quite high, even if there are no differences, if you simply test them with a whole bunch of t-tests. So what you have to do is develop multiple comparison procedures. So you have different procedures where you say, okay, instead of testing each one in alpha, if I do 1,000, I'm going to divide alpha by 1,000. And this is called the Bonferroni procedure. And I'm going to test each one at a very small alpha level. Then you find nothing. So in the one case, you find a lot that aren't real. In the other case, you find nothing, even though you have real ones. So you see that this gets into an interesting procedure of how do we actually make statistical inferences when we have this type of problem. Well, there are solutions, obviously. And you get into concepts that are called family-wise error rates, false discovery rates. In particular, in genomics, we often use the concept of false discovery rates. And in this case, if we're looking at the false positives divided by the positives, we get the expected value of that. We try to control that. But at any rate, that's actually stat 512. So let me just mention one other problem, then I'm going to come back to this. There's also the big N, big P problem. So what is an example of that? One of the problems I worked on where I had that problem was in molecular dynamics. So if you have a simple molecule like methane, and you're looking at the dynamics of that molecule, it only has one dimension if you ignore the quantum effects. It has one dihedral angle that's dynamic. And so it's a one-dimensional problem. But in molecular dynamics, you are actually collecting data at approximately one observation every 10 to the -9th second. So that in 1 second, you collect 10 to the 9th observations. So if you're looking at this particular problem and you only have one dimension, then you have P is 1, but N is 10 to the 9th. But suppose you're not looking at a methane molecule. Suppose you're looking at a complex protein that may have hundreds of dihedral angles, all of which are dynamic. So these molecules, if you look at them, they're very dynamic. They're fun to watch because there are ways to represent them three-dimensionally. And they're very dynamic and moving. But what we were trying to do is estimate the entropy of these molecules, because certain diseases, like mad cow disease, for example, are a problem of misfolding of the molecule. And we can get at those types of things, and misfolding causes a change of the entropy of the molecule. And so if you're trying to estimate the entropy, you have to estimate things like, or at least we thought we did, we have to estimate the multivariate density, which may be, if you have a complex protein, you can have hundreds of dihedral angles. So you have hundreds of dimensions that you're trying to estimate the density, and you have peaks and valleys. Because of the dynamics of the molecule, you get peaks and valleys and so forth. So that becomes a very difficult problem. And so we approached it from a fairly novel point of view using Kth nearest neighbor algorithms. But the point is that we had a situation that we had very large P and very large N. So how do you do it? You can quickly, within a matter of seconds, exceed the amount of memory you have in your computer. So these are the types of challenging problems that you ultimately want to move towards, that you should be able to solve at some point in your life. And these are the kind of problems we get into, or at least talk about, in 624, step 624, which is called high-performance analytics. So there's a bunch of algorithms which are either machine learning algorithms or statistical machine learning algorithms, either what's called supervised or unsupervised learning. In the case of this particular example, is really unsupervised learning in what we were doing, but it was a very challenging problem. So the point is, you have to learn how to represent the data structure. So if you were at the med school and you did an experiment, a microarray experiment, and you just got the gene expression data, then we also have phenotypic data, and that phenotypic data is sort of like gender might be. Whether or not you have cancer is a very gross one, but in other words, it's important, of course. But you may measure a lot of other things. You may measure blood pressure. Some may be continuous. Some may, in other words, you have clinical data in addition. And then you also have other types of data. Because out on the web, for every gene, you have all this literature on that gene, and it's distilled into these databases. And you'd like to connect that data out on the web with your particular genes. So we have this very complex data structure in bioinformatics where we're trying to tie this all together. But in the simple case, you're just trying to tie the phenotype data with the genotype data. That's the simplest case, and that's what we're going to look at here. And we're going to look at a very simple phenotype. So the question is how do we self-describe this data structure? So how did they do it in an expression set? Well, we're going to kind of mimic this here. So I'm first of all going to have a descriptive file. I'm going to have a description type entity that describes the phenotype. And let's assume that for the phenotype, we simply measure the age and the sex for the phenotype data. And so what I'm going to do is I'm going to create a character vector right here. I'm going to create a character vector. Now, character vector, the first vector, and this is self-describing as you understand, it has sex, and then it says that M equals male and F equals female. And that's all in quotes. So that's describing the first phenotype variable, which is sex. And the second phenotype variable is age, and here we're describing it age in years. So we know that we're using M and F to represent male and female. We know that age is measured in years, not months, not something else, but in years. So at this point, I'm going to put a name on it. And then I'm going to give it a class, var, V-A-R, for the variable names. And then var L, S3 for S3. This is going to be an S3 class. So I define the class. And what does it look like? It looks like that. That's the print representation of it. That's the default print. So it says the actual data is this middle line. That's the actual data, but we gave a name to each of those, and then it has a class attribute. Okay? So what we now have done is we have a descriptive file that describes the phenotype data. That's what we've done so far. Now, let's suppose we're going to have right here that sim, and this means simulation because we're going to simulate the data. In fact, we're going to simulate everything here. EXPRS, sim expressions, is a matrix containing the simulated gene expression data. Okay? And then SimPD is a data frame. So we're using different data structures. In other words, the expression data is in a matrix. The phenotypic data is in a data frame. So the SimPD is a data frame containing the simulated, again, phenotype data. So how do I construct those? Well, we're actually going to construct, I'm going to set a seed. We're actually going to simulate this. Okay. And so here's my simulated data. Now in the book they actually have an error. They have 10,000 instead of 1,000. I'm going to simulate from a gamma distribution that has a shape parameter 500. So 500 is actually the shape parameter of the gamma. So the gamma distribution is a positively skewed distribution. So this might be reasonable for expression data, that it's a positively skewed distribution. It starts at 0. It goes up. It sort of looks like a chi-square if you know what it looks like. So it's a positively skewed distribution. So we're going to assume our phenotype, our genotype data is positively skewed according to a gamma. And the shape parameter gamma is 500. And we're going to simulate 1,000. And we're going to form that into a matrix that has 10 rows and 100 columns. So this would be like having 10 patients and 100 genes. Okay? So if we had 10 patients and 100 genes, it would be sort of like this. And so I actually can print it all out. And there it is. Now you notice something here. Can you tell me what, if I have 10 patients and 100 genes, does that kind of look right? The way you would classically do statistics? It would be the transpose of that matrix. You would have 10 rows and 100 columns, not 10 columns and 100 rows. But this, in fact, is the way that expression set works. It gives the genes as rows and the patients as columns, just the reverse of what we usually do. But the reason is because, think about it, on a computer screen, if you had let's say 1,000 genes in columns, it would keep lapping back on top. In other words, to get one row, it would have to print out many, many things. So it's easier to represent it this way in terms of how you visualize it. And so this is true in expression set also, in the real expression set, not the one we're sort of creating, is that the genes are rows and the patients or whatever, the samples are the columns. And so these samples might be tissue samples from patients, typically. So that's just, notice that again, that's the way we're representing it. And this will be interesting when we sort of check things out in a minute. Now, what am I doing here? So let's look at, whoops, no, wrong place. Let's look at SimS. Now, what we did here is we have a character vector M and F that has 2 elements in it. I'm going to randomly sample 10. Actually, after all, I have 10 patients, right? What I'm going to do is randomly assign male and female to each of those 10. That's all I'm doing. So I say replacement equals true. So I'm sampling 10 from 2 with replacement. So the first time I sampled, I got a male. But I always have male and female because I do it with replacement. So each time I'm sampling each one with probability of half. Now, you're kind of interesting here that we got this nice pattern here. That was totally by chance, I hope. So, okay, and now I'm going to do sim age. So what am I going to do on age? Well, let's look at sim A, S-I-M-A. What we're doing is we're assuming all patients are between 30 and 45. So all these patients between 30 and 45. So I'm going to randomly sample 10 from between 30 and 45 inclusive with replacement. And so the first patient is 42, the second is 43. Okay, the first person is a male who's 42. The second patient is a female who's 43, and so forth. Is it clear what we're doing? Now, we're going to put this into a data frame. So how do we put it into a data frame? We simply use the data.frame argument function. And so I'm going to execute this. And then this is what the data frame looks like. So I just use data.frame, sex equals sim S, age equals sim A. And that gives me, this is my phenotype data. Now, in real experiments, your phenotype data may be much more complicated than that, and hopefully we have more than 10 patients. But you might be surprised that a lot of these studies that are done have relatively small samples. It drives statisticians crazy. You know, you have 5 observations of this and 5 observations of this, and I have 5,000 genes, and I'm going to make all these inferences based upon a sample of 10. It's scary. I mean, the reality is, what you're going to do is find the big differences. But you're probably not going to find the more subtle ones. So, okay, so we've generated these data structures. Well, if we were doing S4 classes have a constructor function called new that will create a new instance of a class. So, but that's not true for S3. We have to develop our own constructor function. So we're going to create a constructor function called new.expr S3, S3 for S3 class. So we're going to do a constructor function for this. And how do we do this? Well, all these if statements at the beginning would not be necessary in S4 classes. The reason is S3 doesn't do any kind of checking for you, whereas S4 does. And so S4, that's why it's more reliable, because if I make mistakes, S3, you may not catch it in the code if I make mistakes. But, so we're going to put in some code here that checks for the possible errors you may have. For example, eData. Now, eData is going to be that simulated expression data. So what are my arguments? My arguments are the class. I'm going to send its class. eData, pData. The eData is for the expression data. The pData is for the phenotype data. Now, these are arguments, and these are internal variables within this. So I'm going to actually pass it the eData and the pData and so forth. And then that descriptive file is the first one we did, the description. The C descript is for the description file. So how do I do this? Well, first of all, you know, I can go in and just go ahead and do this. I can execute it. And so now I have a constructor function. You know, now I have a constructor function down here. But let's look at the logic of this. So one of the mistakes you may make is the expression data you may be saving in a format that's not a matrix, like a data frame. So it says, if it is not a matrix, if eData is not a matrix, then you stop and print out invalid expression data. Okay? And you stop. In other words, they're going to have to coerce it into a matrix. Now, sometimes you can write code that checks it to see if it's in a data frame and it's all numeric. You could write code that would coerce it into a matrix if you wanted to do that. Sometimes you'll say, okay, you can enter your data as a matrix or a data frame, and if it's a data frame, I'll coerce it to a matrix, because ultimately you may need to use it as a matrix in terms of statistical computations. Okay, now what about the p-data? Okay, well the p-data is supposed to be a data frame, right? So I say if the p-data is not a data frame, then stop invalid phenotypic data. You see what we're doing here? We're doing some checking. And then the next one says, what about this? Well, the C description actually belongs to a class called VARLSS3. VARLS3. It belongs to that class because we define that class. If you look at the code up here, we defined it with a class variable up here. So we check and see, is it of the correct class? So here we say inherits. Does C description inherit from that VARLS3? Okay, if it does not inherit, then I stop invalid covariate. That COV means covariate description. We can think of these as being covariates to the gene expression data. And now I get the number of columns of E data and the number of rows of P data. And what I'm claiming is that the number of columns of E data better be equal to the number of rows of P data. Why? Can anyone tell me why? The E data is, let's say we're talking about tissue samples from patients. The columns of the E data represent the patients, right? And the rows represent the gene expressions. But what about the phenotype data? Well, that's the more normal way we do it, whereas the rows represent patients and the columns represent the phenotypic variables that you're measuring, okay? And so it better be the case that the number of columns of the E data must equal the number of rows of the P data, because they both represent the same group of patients. So here we're checking to see if that's true. If it's not true, then stop incorrect dimensions. So all of that code was just checking to make sure we didn't have a mistake. Now what am I going to do? I'm going to create a data structure in a list that contains not only the phenotype data, but the description of the phenotype data. So what I'm going to do is form a list, and the first element of the list is the P data equals P data. So the element is called P data, and that element contains the phenotypic data. And the second element is called phenodata, called var labels, VAR capital L, ABLES, ELS, and it's the C script. So it is what? It is that class instance that is of the VARLS3. So in other words, PD contains both the data and the description of the data for the phenotype. Is that clear? Now, I haven't done a corresponding thing for the gene expression data. If the genes are listed, and suppose you wanted to put some description of each gene, do you know how you would do it? Well, you can find it out on the web. And one of the interesting things about R is it's very good about going out and scraping, pulling stuff out of databases or scraping stuff out of the web. And so I could actually go into various databases and pull out descriptions of each of those. I could actually pull the names of the genes, but the names aren't very descriptive. So I could also pull some descriptive information about each gene. And the way I would do that is have some R code that would go out into these public databases, and it's talked about this later in the book. We could go out and pull this public data in that we can actually have a descriptive information for the expression data also. Now, the data can get complicated. So this data is more complicated than some types of data. But the data can even get, more complicated, because you may have drug data in which you may have a bunch of chemicals, and then you may also have biological data, and then you may look at the interaction between the drug data and the biological data in what's called a graph. And if you do that, you have this interaction data, and this type of model, we can now build models that are very complex that take in the interactions between, say, the chemistry and the biology. This is the kind of research that Mark Culp does. Okay, we're moving along. Fortunately, our data is a little bit complex, but it's not so much. But the idea is that we want a data structure that is, in fact, very descriptive. So what's the next step? So we've got this constructive. Oh, no, I haven't finished the constructive function yet. So right here, and that's line 121, I actually have created this list that contains the phenotype data, both the data and the descriptions for the variables in the phenotype data. And then I define a class for the phenotype data. I say the class of the PD is pheno, it's got an S3 on it again, so it's PHENODS3. Again, it's got that S3 that indicates an S3 class. You don't have to. That's just was done for, so that you know that that's S3 class, but that's certainly you don't have to do that. So now I've defined the class, and now I'm going to create a list that has both the genotype data and the phenotype data in the list. So I have a list that says ANS is a list that has the first is expression data, the EXPRS equals E data, and that's a matrix. And then the pheno data is, in fact, this other, it's a list within the list because it has a class structure. And so that is the second element of this list. And then I'm going to define the class of ANS as whatever I pass to it as the class name. So this actually gives me a general structure for creating these and lets me pass class names. So where did I get class? Where did I get E data? Well, that's in the argument. So I'm going to pass it a class name. So I'm going to name this overall data structure whatever I want to call that particular class that has everything in it. And then the E data was passed as a matrix, but that was defined as the first element of this ANS. So I'm passing an E data. So how do I pass this information? So I'm going to create a new. So what I'm going to say here is that I'm going to make a new instance of this. I'm going to call the class expression S3. So that's actually the class of this whole thing, is EXPRS3. And then I'm going to pass it the data I generated for the expression data. That was the 100 by 10, right? 100 rows, 10 columns. And I'm going to pass then the sim PD and let's see, did I define that externally? Yeah. Sim PD, that's the data frame, yeah. And then I'm going to pass the descriptive information. So let's go ahead and execute this. And then if I look at this structure, it has it has up here, which is typically you don't want to print this out. You particularly don't want to print this out if you've got lots of data. We're kind of at the upper limit of what you might want to print out. So that's the expression data, and below is the phenotype data. So are there any questions? So this is sort of what is done in the bioconductor with the expression set. Now they're using S4 classes, so they're not doing it the same way. And it's richer. This is very much of a simplification of what was done for the expression set in the bioconductor project. But this is sort of the idea. So the underlying idea is that we want a data structure that describes the data, and we want it to be self-describing. So we want it to be self-documenting. So we can extract the documentation about the file from the file. Well, in this case, it's an object, and it has a particular class. Now you notice all of the information that it's giving for the phenotype data. Okay, any questions on that? So that's something you might want to study a bit. But there is an issue that I'll discuss. There is an issue with this representation. And the issue is this, and I'll come back to this. I have an object called myES3, and you would think that if you did myES3 that I could extract with a dollar sign. You would think that if you look at the way it's constructed, that I could extract, for example, PHENO data. But it won't. And the reason is because the way this is constructed, it's actually constructed this as if its character with this whole first thing. Notice the quotes here. There's also a quote at the beginning. Notice the quote before the list and the quote at the end. It actually has represented this as a character vector with two elements. And so if I actually go in and say my ES3 then I actually get it just by using the square brackets as the subset operator. But I would claim this is not really what he wanted to do. Because what you really want to do is return a list that contains the actual components in the list that you can extract with a dollar sign. Now the reason I know that he wants to really do it that way is because he has a homework problem that wants you to do it that way. But it doesn't work. Okay, we'll come back to that later. Let's talk about generic functions and methods. So when you have a generic function in S3, what happens is you make a call to use method. And that use method indicates the dispatch. How do I dispatch? Because I have a particular method. The argument, the first argument, in S3 it's almost always the first argument. It looks at the class of the first argument, and it dispatches based upon that class. So we're going to see how this works in just a little bit. So that's sort of the idea. Now, when we create this generic function, we need two arguments. We need x, which is going to look at and say, well, what is the class of x? And then we could have other named arguments. But a lot of times we don't know what we want, and we may want to extend it, and we use ... to indicate any other arguments that you may have just get passed through by this generic function to the real function that gets called. So what's going to happen is you have a generic function, but ultimately a real function gets called. And that function may have arguments. So if in addition to x, I give these other arguments, they simply get passed through to this other argument. That's what the three dots mean. It's a little confusing, but it basically means, depending on what gets called, I may have different arguments. I don't want to specify the arguments here necessarily, because based upon the dispatch, there are different functions that can be called based on the class, and those might require different arguments. So what I want to do here is I may give those arguments, but they simply get passed through to the real function that gets called. Okay? I don't know if there are any examples of that, but we'll take a look at it. So that's sort of the idea. So let's take a look. I'm going to define a generic function right here. And we almost always define a default method. In other words, suppose you cannot find a class that matches. You can't find a dispatch that correctly matches the class. Suppose that you can. Then it defaults back to default, the default class. Now you can think of default as sort of being a class. But that's what's going to happen. So you should always have a default method. But you probably want a more specialized method that's more specific to what you want to do. Because the default method is sort of going to cover any case that kind of falls back to it. So I'm going to define a generic function. And so the only thing I need, and they're usually something like this, is x comma dot dot dot. Dot 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 is sort of that captures any arguments you may pass to the generic function, and they simply get passed through to whatever really gets called. And then the use method, and you say use method fun. And what that does actually is looks at the first argument, it looks at the class of that first argument, and it simply dispatches on the basis of the class. Now that will become clearer in just a little bit. So I'm going to have a default method that says fun.default function x, and here I'm going to again just use dot dot dot, and it says print in the default method. So this doesn't do much. So at this point, this is all we have. So if I say fun of 2, well, there is nothing, we don't have any other methods defined for this. And so this is all we can do is go back to the default. So that's it. But suppose we define a couple dispatch. So, and the way we do this is, just like I said, that default sort of acts like a class. If I have fun.foo, foo is going to be a class. So if I have an object of type foo, it calls that function. Also, bar is a class. If I have an object x that's of type bar, bar gets called. If the class of x is fun.foo gets called. If it's do you get the idea? So I'm going to create 2 functions, and those are going to correspond to 2 classes, foo and bar. So what does foo bar? So here's foo bar. Let's execute this. So foo bar says it's the function that gets dispatched to if the object is of class foo. So, and that notation is what you need. Fun.foo. The function name dot the class name. And then x gets passed through. Now, if I would have had any other arguments, suppose that function would have had some additional named arguments, or additional arguments even if they're not named. That dot 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 in the generic would simply pass them through to that function. But in this case, there are no other functions. So what this says, function x says print start at fun.foo. Then it says next method. We're going to get to that. And then it says print into fun.foo. And now let's define another function for the class bar that says sort of the same thing. Start of fun.bar, next method, print into fun.bar. Now to do a little bit of mental gymnastics. Let's say x equals 1, and let's define the class of x to be foo, comma, bar. What am I doing? I'm saying that it's the most specific representation is foo, the more general is bar. So I have inheritance here. Foo inherits from bar. Something that's in bar may not be of type foo, but something in foo will be of type bar. So I've defined foo and bar to be classes, but they inherit from, bar. Foo inherits from bar. And now I'm going to say fun of x. Why did that happen? Well, the key of why this happens is next method. Next method, if I'm in foo, the next method goes to bar. It goes from the most specific to the least specific. So if I'm in foo, the next method jumps it to bar. If I'm in bar and call methods, where do you think it jumps it? To default, which is even the most general. So let's just sort of step through this. Okay. So what happens? When I call fun of x, it says it first of all calls the most specific, which is foo, right? So it calls this first. In other words, it calls fun.foo. So it says start of fun.foo. That's the first line. Okay? Got it? Now, what's the second line of this function is next method. Well, what is the next method? The next method is associated with bar. It goes to the less specific. It goes from here up to here with next method. So now it then calls foo.bar, which prints the start of fun.bar. So that's the second line it prints. Okay, what happens now? Because this one now calls the next method. But the next method is actually the default. Okay, so the default says that it's in the default method. Now, once we've done that, once we've defined in the default method, then it drops down to this print right here, end of fun.bar, which prints out this, and then you go back to this function where I called next method, and then print out end of fun.foo. That's a little tricky because I'm jumping back and forth between these functions, but it's kind of fun, isn't it? So, I mean, if you don't understand the next method, you are not going to understand what's happening here. Okay. So again, the key next method is very powerful. It lets you go up. It lets you go up from the most specific to the least specific in the hierarchy. In this case, in the inheritance path. So it goes from foo to bar to default. So if I only had one class, if I didn't have a foo and a bar, if I only had let's say a bar, I only had one class, and I have a function associated with it, and I called next method, it would go to the default. So it might be a default method has some basic computations in it that you need. You may have a basic class up here, and then you have various ones that come down from it. And from that, if you then could call up to these same basic functions. Okay. Going back to our example, suppose you want to create a print method for the phenotype data. Now, the little problem you have with this example is I'm going to pass it an object of type phenotype. Okay, so I'm going to pass it an object of type phenotype. And then how is it going to print it out? Well, if this object has the pheno-p data in it, then I can extract it with the $sign operator. But again, you have to do that in the right way. So in other words, the object I pass it has to be in a list form so that I can use a $sign to extract it. And so I can extract it and get the dimension of the phenotype data, which in our example might have been, what was it? There were 10 rows and 2 columns. The 2 columns corresponded to sex and age. And then cat concatenates together character strings. So I can take instance of phenodata, notice the character string, and then comma, and then it has the dimensionality. It has dm2. dm2 is the number of variables. So what dm2 does, it says it's the number of variables that I have, and so it evaluates that, and it gets coerced to a string. In other words, this cat will coerce a numeric value into a character string. So what happens is I'm concatenate together the first character string. I evaluate dm2 as the second argument of my phenotype dimension. And in our case, it would be 10 by 2, so it would be 2. So this would read something like instance of pheno S3 with 2 variables. That's what it would tell you. It would tell you the number of variables. So that would be the first line. Then the next line would say, okay, and dm1, the number of cases. So it would say and 10 cases. And then if I extract the variable labels from that data, okay, if I extract that from the object, and then I could, the /t means a tab, and then that would simply give the variable labels, and the /n means a new line. So it would drop down to a new line. And then I'm just sort of going through how you might write a descriptive file that's a pretty print. In other words, it prints descriptive information more so than the default print you would get if you didn't do this. And then you have the names of VL. You define as MN, and then you do a sequence along VL, and you specify the names, the VL. You're going by I now, and you're using nothing to separate. You use a colon, so you have the name colon and then VLI. Okay. It's going to take a little bit of work, though, to get this function to work. The function actually will execute, but it won't run directly on our data that we created previously. So I'll have to take a look at that. Now, if I want to do the expression data, again, this is a print for the expression data that gives you what you need. So, at any rate, are there questions on this? We can take a look. Okay, I'm going to stop here. Okay. I'm going to look at this a little more. There's not much more to do in this chapter. In this section, there's a little bit more to do here. But those are the key concepts we just went over. What I'm going to do next time is look at S4 classes. And a little bit of finishing up here.